Okay, YouTube, in my last video we defined what we mean by quadratic functions, and we say that these are functions of the form f of x equals ax squared plus bx plus c, where a is not 0 and our highest degree on our terms is squared. So these are square-like functions or quadratic functions that look like parabolas, okay? What we know though is this. We say that we know how to graph quadratics very quickly when they are in standard form, and standard form would be this other form of this equation that we could rewrite it as, where we would know exactly how far left and right it would shift, how far up and down it would shift from its parent function, which is centered at the origin here. So we could say literally that the vertex is at hk, and then we could also say, well, then the axis of symmetry must split this right down the middle, okay, and go through the same x value that our vertex has as an x value, and it would be x equals h here. So our goal is going to be able to rewrite this into this form by using a process that we call completing the square. So completing the square, one thing I just want to kind of note here is this. When you look at this equation right here and we want to rewrite it into this equation right here, I would say that anything in standard form is going to have some x minus h quantity squared, okay, some binomial squared. So really quickly before we get into completing the square, what I want to look at or notice is the patterns that exist when I have binomial squared, and how we could necessarily work backwards. So let's say I have, like, let's go x plus 2 squared, we'll go x minus 4 squared, and then how about x plus 10 squared? If we were to square these out, remember you cannot distribute that squared through. We actually have to FOIL this. And so in this first instance, I'm going to get x squared. I would get 2x and 2x would give me 4x, so I'd get two of those 2x things. And then here I would get 2 squared, which is 4. How about if I were to square the x minus 4 here? Well, x minus 4 squared would be x minus 4 times itself twice. Then we would say, well, I get x squared, foiling this, and then I'm going to get minus 4x and minus 4x. So basically, two of these negative 4x things is negative 8x. And then the last term here, again, is going to be positive, and it's going to be 4 times itself. So we say 16. And then last but not least, if I were to square this x plus 10 squared, x plus 10 squared. What's the patterns that I'm seeing here? Well, I'm going to get x times x, which is x squared. And then I'm going to get two of these 10x things, so I'm going to get 20x. And then I'd say, well, the last term is always going to be this last term times itself. So it's always going to be a perfect square of a number. So if I said looking at each of these instances, the thing I want to point out is this. Every one of these terms, these last terms, these constant terms, is always a perfect square. And if I were to say, well, what is it a perfect square of? Well, in this case, it was a perfect square of 2. In this case, it was a perfect square of negative 4. And in this case, it was a perfect square of positive 10. How do these terms in these parentheses right here, this term right here, how does it relate to this middle term right here? And what I want to point out is, essentially, is this. We have some expression, ax squared plus bx plus c here. And what I'm going to say is that the c value is always equal to half of the b value, which was this number in here. Notice that this number in here is always half of the middle term, since we had two of those when we multiplied o and I together and combined like terms, always in the middle. So we say it's the c term is always equal to half of b squared. And this is the note that we want to make here. But basically, if this is true, then we could say that this thing is considered to be a perfect square trinomial. And not only is it a perfect square trinomial, it'll factor into some binomial times itself. And not only that, will it factor into some binomial times itself, it'll factor into something that we can write in this form, which is a binomial squared, which is the key characteristic to standard form. So that is to say, if I had some x squared plus, let's say, 12x plus some constant here. Let's answer this question. What would I really want the c value to be equal to so that I could rewrite this in this form right here, okay? So according to what I've got written here, we would say, well, what I want c to be equal to is half of my middle term, and not just half my middle term, but half my middle term squared. So I would say, well then, what I want c to be equal to here is equal to 12 over 2 squared. And in this case, I get 6 squared, and I get 36. So we would say that if this were x squared plus 12x plus 36, then what we could do is we could rewrite it into this form. And even better, we say, well, then what number would go in here? What would it factor into? Well, what I can always tell you is it factors into x plus b over 2. Or this number here, notice that this 10 is half of this 20. Or we'd say that this negative 4 is half of this negative 8. Or this positive 2 is half of this positive 4. Or half of our middle term. In this case, half of our positive 12 would be a 6. This would be a really quick way to rewrite it this way. So when we complete the square, let's go ahead and consider this expression over here. We have f of x equals x squared minus 6x minus 1. So we could rewrite this if you want as y equals x squared minus 6x minus 1. But what I notice is if I tried to factor this right now, it won't factor this trinomial. I cannot think of two factors of -1 that when multiplied to -1 add up also to be this -6. And even worse, we want this to factor into a perfect square binomial anyways. We want it to factor into something like this. So the first thing we're going to do is we're going to take this constant term right here and we're going to boot that loose term over to the other side. So what I end up with is now this y plus 1 on the left, and I'm going to get this. We get x squared minus 6x plus, and I'm going to put a blank here. So essentially what we're going to do is we're going to ask this question. We say, what would I really, really, really want to have here so that I could factor this into a perfect square binomial? And according to our rule over here, this is our rule for perfect square trinomials, this c value right here, we want it to equal half the middle term squared. So we'd say, well, what's half of -6? And half of -6 is a -3. And -3 squared is a positive 9. So I'm going to add a 9 to the right side. That's as easy as completing the square. Okay, that's what we're doing when we complete the square. So we booted the loose term, and then we add in this constant that we want. Now, one note that I have to make here is this. You can't just add a constant to one side and not add it to the other. So we certainly need to add this 9 to the left side as well. So now the right side, what I want to see is the consequence of doing this was essentially that I can now factor this into a perfect square binomial, where what goes in here, well, what goes in here was half of the middle term that we squared to get the 9 in the first place. So this half of -6, this is really important, but it's actually got to be a -3 because half of -6 is -3. And on the left side over here, we get 9 plus y plus 1 is really y plus 10. So the last step we'll take here to get this into standard form is essentially we'll boot that loose term back over and we get x minus 3 squared minus 10. So if I said, okay, what I want to do now is maybe go graph this, one thing I already know then is that this thing is going to have a vertex at a value of 3 comma -10 at h comma k. And I say a positive 3, -10, because in our formula we have a negative here. It's going to look backwards than what it really is. So if this looks like -3, it's really a positive 3. So I would go right 3, 1, 2, 3, 5, 1, 2, 3, 4, 5. We would say here's our vertex, and this is at 3 comma -10. As far as what our a value is in the front, our a value is 1. So just like our parent function, it hasn't been stretched. It's going to go up 1, right 1, and I can say that this point right here is on my graph for sure. This would have to be 4 comma -9. And because we have symmetry here down the middle, we say what is the equation of this axis of symmetry? We say the axis of symmetry is that x equals what? Well, it'd have to be 3. It'd have to be the same as our vertex x value here, okay? And then because of symmetry, I know that this point here, 2 comma -9, must also be on this graph. So we'd say here is the graph of this parabola that has a domain of all real values, and it looks like a range of from -10 up to infinity, okay? In the next video, what we're going to look at is how would you complete the square when you have a trinomial where the a value is not equal to 1. Cheers.